Hello everyone, this is Mohammad Rashid Khan Menon, and my paper is accepted in 8th International Conference on Computer and Communication Engineering 22 to 23 June 2021, Kuala Lumpur, Malaysia. My paper title is ECG Electrocardiogram Digital Signal Processing for the Biomedical Applications. Mohammad Rashid Khan Menon, Mohammad Baklesur Rahman, and Hyung Gyun Ryo, Department of Electronic Engineering, Changbuk National University, Cheongju, Korea. Outlines of my paper are Introduction, ECG signals with noise sources, adaptive noise reduction, result and discussion, conclusions. In introduction part, biomedical signal processing has significant research value in the fields of life science, clinical diagnosis, disease prevention, and medical instrument production. Biomedical signals originate from human life activities. There are diversity and complexity in processing. The signals using computers has provided greater strength to diagnose using powerful algorithm for biomedical signal analysis. Electrocardiography is a graph for voltage versus time of the electrical activity of the heart using electrodes placed on the skin. The minor deviation of skew in the normal rhythm of the electric potential is the identification of the various types of disease. The noise approximation and its application in adaptive noise reduction are evaluated using signals recorded by both dry and wet adhesive electrodes. Now, ECG signals with noise sources. This is time versus amplitude. ECG signals contaminated by motion artifacts. These artifacts are caused by the electrodes movement away from the contact area with the skin. Now, baseline wandering from 3 power line interference in this figure. It is mainly caused by changing of the body electrode impedance, which is reflected in the form of low frequency component added to the signal. Impedance changes are caused by patient's respiratory movements or any other smooth movements that affect the electrode skin contact. Now, in figure 3, power line interference added to ECG signal. 50 Hz in this case, the kind of noise is originated from the power line electromagnetic field. Depending on the utility, electrical network frequency used, the nominal frequency of the alternating current overlap with recorded ECG signal through capacitive and inductive coupling. Now, in figure 4, two different intervals corrupted by EMG noise from the origin. The electromyography signal is produced by the skeletal muscle contractions. The recorded electrical activity is generated by the muscle cells when these cells are electrically activated. Because of these muscles are in the vicinity of cardiac muscle, it is expected to catch the EMG signal while recording ECG signal. The amplitude of EMG signal is stochastic. However, the amplitude distribution of this kind of noise could be reasonable, approximated by a Gaussian function. It can range from 0 to 100 millivolt. On the other hand, the amplitude of ECG signal ranges from zero point 0.1 to 5 millivolt. This means that ECG signal could be completely obscured by the EMG noise. Now, adaptive noise reduction part. These are two parts: reference signal extraction and adaptive denoising part. At first, in reference signal extraction part, raw signal goes to using MRA to find and isolate possible QRS pairs, and then goes to finding AZVP from 2 square scale of SWT details, avoiding QRS complexes pairs, and SWT of the ECG signal using spline wavelet, and this part is added to the next two part using MRA and finding AZVP part, and then it makes an output which goes to the smoothing part and goes to the scaling part where phi1 and phi2 are added. This part, two thresholds phi1 and phi2 are used to normalize the resulting smooth signal. Reference signal, then it makes reference signals, and it goes to the part adaptive denoising part. At first, this part filtering according to reference signal, and raw signal and filters are added to this part, and then makes the output as a filtered signal. And the equivalent frequency responses of filters at degree 1 to 10 for 250 Hz frequency sampling. A filter bank of 10 low pass filter is used. The selection of the appropriate filters depends on the value of the reference signal at the point. The noise is removed while characteristics of the original signal are retained as much as possible at each interval. The reference signal extracted as a noise level approximation is quantized into 10 levels, and each level is associated with one filter according to the filter strength and to the reference signal value. Filters are applied only when the reference signal has the corresponding value for their activation. And this part, adaptive noise reduction part, this reference signal with and without QRS exclusion. Noisy ECG signal from at the middle part, filtered signal in solid blue, and reference signal extracted with exclusion of QRS components in solid red, and at the bottom part, filtered signal in continuous blue and reference signal extracted without exclusion of QRS components in solid red. And at this result and discussion part, atrial fibrillation adaptive denoising results. ECG signal is at the top figures, and the signal after noise addition is in the middle in solid blue line, while the extracted reference signal red and filtered signal are at the bottom. And the SNR improvement MITBIS record 103 computed for four types of noises. This is the input SNR versus SNR improvement in decibel, where there are four types of noise: muscle noise using function, white Gaussian noise, brown noise, and pink noise. We see that whenever we increase at the input SNR at -5 to 25, then the SNR improvement is decreased gradually uh, from 32 to -4, and at this result, whenever in figure 11, that is the MIT BIS record 106, at this types of figure, we see that the SNR improvement is increased from 103, and then is more increased from uh, in 117 records from the other two records, and that's why we get a single lead delineation result with and without the uses of adaptive denoising. In this part, whenever SNR is -5 and to SNR 10, and MIT BIS record 103, 106 and 117, and uh, at this part we see that the at whenever SNR is -5, then the raw signal value 98.110 in pp per percentage, and then SN per percentage is 99.808, and denoise signal 99.521 and 99.906, and improvement is 1.411 and 0.096, and whenever SNL is 0, then the improvement in 0.048 and minus 0.048 in cent per percentage, and uh, we see that the in MIT BIS record 106, it is a gradually increased from 103 in the pp percentage and cent percentage, and 117 in the record. We see that this is gradually include in improve in improvement of SNR, and that's why whenever we increase SNR 0, 5 and 10, then this is decreasing in improvement gradually in this part, and finally at the conclusion part, noise reduction in the ECG signal is addressed in this paper. Adaptive noise reduction methodology could be used and customized to operate on fatal ECG signals. Check the function of an implanted pacemaker. Check the effectiveness of certain heart medications. Study the side effect of new medications on heart muscles. Thank you very much for kind attention.